after lunch. So our next speaker is Shuang. He is a junior fellow here. He was years ago, well, not years ago. He was a little while ago a student of Peter Keynes, was a postdoc there, and is now a junior fellow, and he's actually on the job market. So if any of you have jobs, he might be interested.
Thank you everyone for being here. And I also like to take this opportunity to thank the organizers for organizing this fantastic workshop. I learned a lot, and thank the organizers for inviting me to speak here. So today I would like to share some initial investigations, and it's also part of my learning process of starting epidemic models, where we identify a connection between the epidemic models and the neural networks, which to me is fascinating. So this is joint work with Peter Keynes. Okay, so I will briefly spend some time to explain what are the type of widespread model on networks that I will be talking about. And then with a different view of the same model that leads to a neural network representation. And then we will discuss the properties of this model, which we call it transmission neural networks, short for TransNN, and both as widespread models and as learning models. And then I'll conclude the talk and discuss some ongoing investigations. So as we know, when we study widespread models on networks, the local graph structure are actually very important. In practice, for example, when we do context tracing, after we identify an infected individual, we do an interview to identify who the person has actually in contact with. And then we inform those people who have potential exposures and ask them to do isolations or do test. Another example is ring vaccination. If we identify an infected source, we can do a strategy where vaccinate its immediate neighborhood or second hop neighborhood. So in this way, we can contain the virus on a local scale. Another example is that's actually used in practice is this COVID exposure notification system, which is a mobile application on your phone, and to use Bluetooth signals to identify distance between individuals. And for people who are using this application, if they test positive and report the result to the system, and then the others who are in contact with this person will receive a notification saying that you have potential exposure, and then you should either do test or do self-isolation. Another related, but in a different context, is computer virus spread, where we have some sort of idea of how the computer are connected. So they're on the computer network, and if there are some source of infection, we can predict or estimate the probability of some computers that are vulnerable to attack. So all these examples use some sort of the underlying idea of the transmission network to help us predict, monitor, or prevent virus spread into a larger scale. So there are tons of work that's been done modeling virus spread on networks. I only list a few of them that is closely related to the work that I'm going to present. In particular, the first one I listed here is an epidemic model with heterogeneous transmission rates across different groups. This is done by Leon Manovich and York. This is probably the first paper that gave a thorough treatment of these type of models and identify the threshold condition. Another related topic is on this discrete time virus spread model, where one knows the exact network structure and want to say something about the threshold condition. These two type of models fall into the category of mean field approximation, or where it assumes independence of among the nodes. And then some people have done some work to study the approximation error accuracy for mean field approximation. And as we have seen in the previous talks, an interesting problem would be when we look at the networks, we don't know the exact structure, but we have some information to summarize the networks, either through some random connections, through some degree distribution and others. We can still infer properties about the virus spread. An important method that's related to closely to the work here is the message passing message, where given the network structure, individuals or like we compute the probability of node I infecting node J, and then it's called the message. We saw it through a self-consistent equation. And based on that, individual nodes summarize over its neighborhood to compute the probability of infection. So as I mentioned, I did not list, this is by no means a full overview of the vast literature. I just point you to some references here for other related work. Okay, so I would like to start with an ideal example where we know the transmission structure. So here I define an effective transmission link from node I to node J if a virus passes from person I to person J that actually caused the infection of node J. So this is sort of, we have a full information of how the virus spread on the network. And then each node has two states, infected, uninfected. I denote Pi, the probability of node I being infected at time K. So we know that with that, one can write the one-step update of the probability of infection. On the right-hand side, this is the probability of none of my neighbors are infected. And on the right-hand side, this is the probability of node I not being affected. Here, the only extra point one need to pay attention is that the neighborhood of node I here, I define it as the neighborhood with itself included. This is just use this just to make sure that characterizing the fact that individuals after infection do not recover in just one step. Now, that is very simple. Now I want to take a different perspective of the same problem. Instead of associating each node with their probability of infection, now I introduce a new variable that to associate with the state of the particular node. This I take the minus log 1 minus Pi. You realize that this actually is the so-called information content or channel information of the event that node I being healthy at time K. So with this transformation, we see that it is monotone, bijective, and concave. What we do is we take log on both sides of this equation and take negation. Now we arrive at linear dynamics with the state as the information content state. For linear system, we know how to analyze. We can even write out explicitly the solution for the SKs. So it's just take the power a to the power of km times the initial condition. And with the same equation relation, we can go back to the probability of infection. So we have now here the message is that we take a different perspective, we get the linear dynamics, it's easy to analyze, and we can get explicit solutions. But now in the real situation, we don't know exactly the network structure. Then you just introduce some random or connections among individuals. Here I use this picture to illustrate a physical contact network where two persons have a connection if they are within a radius, say 6 feet for 15 minutes at least. And then again, each node has a probability of being infected at time K, denoted at PIK. On each link, multiple viruses, particles are sent into the common space. I denote the Aij as the number of particles sent from node I to node J, node J to node I. And Wi represent the probability of each of these particles sent from node J that is successfully received by node I. So following the similar ideas, I read the same type of equation, where on the right-hand side, this is the probability of none of the particles, virus particles, reach node I. And on the left is then the probability of node I being healthy at time K plus 1. Here that I make an assumption, the independence assumption on the variables. If you think about independent, each individual has a random event associated with it being healthy, and then this was ignoring the dependence of across different individuals. And also assume the conditional independence of the transmissions across different links and the transmissions across different various particles. I want to spend a bit more time on the interpretations of this model. It has the property, the dynamics has the property that I'm an individual. One of my neighbor is enough to infect me. So this type of dynamics has this property. With different interpretations of the AIJ, WIJ, and PI, we actually can treat it for a different application problem. I start with the case where we think about a contact network where we study the probability of individual getting infected. In fact, one can also think about it as populations where each node is represent a city, and the AIJ then naturally represent the number of passengers from node J to node I. And WIJ then represent the probability of each individual passengers from city J that infects someone in city I. One can also think about it as some information spread on social network where this represents a piece of information that's reached node I. And then one can, another interesting interpretation is that one can, this with simplifying assumptions could be thought of as a connection between two neurons at the neurotransmitter level, where this is a picture of a typical illustration of a chemical synapses.
That's your product over I and I. There's a J in the product and a Q there.
Yeah, thank you. So this should be J. Thank you for. Yeah, this should be product times all the individual neighborhoods and their particles from the universe. Yeah, so as we see here, on the left is presynaptic neuron. After excitation, it would send a large population of these molecules called neurotransmitters into the common space called the synaptic cleft. And then each of these neurotransmitters has some probability connecting with these receptors on the postsynaptic neuron, then activate the postsynaptic neuron with some probability. Now I want to use the same type of idea that we studied for the trivial example we start with. We view the system from a different perspective. I use the information content as the states. I take log on both sides of this equation and take negation on both sides. So here it also has to be J. And then we arrive at a new form of representing the dynamics, where the only actual part is this psi function. It's a nonlinear function that takes an activation level parameter Wij and takes the signal input as J. We call this function psi here the tunable log sigmoid activation function. I will explain a bit later why we call it, we give it that name. But it has the property when W equal to 0, it represents a 0 path. When W equal to 1, this is a full path. When W between 0 and 1, this represents a passive path. It also has the nice property where this function is concave in X, which we will use in deriving the threshold condition very easily. And then it has the property that one can write all the explicit derivatives. So I want to relate this to a standard view of the neural network that people use nowadays a lot. The connection can be done through as follows. First, we give a homogeneous parameter for all the Wij's, and then we define a new state, which is the activated state passed through this activation function with the homogeneous parameter W of your signal. And we can denote this by sigma W, some nonlinear function activated on the states. Now we just plug in this nonlinear function on both sides of this equation, we get this. What it says here, you do a linear summation over your neighbors, and you take a nonlinear activation function, produce the output for that particular node. This is a standard neural network unit, right? So now we see the connection. If we specialize in the parameter W to 0.5, we get this form, where this is actually the log sigmoid activation function, and this is some constant offset. So this is the reason why we call it a tunable log sigmoid activation function, because you get a flexibility of choosing the parameter. To summarize at this stage, we start with a virus spread model look like this. We take a different view of the same model, taking the nodal state to be the information content. We get a simple dynamics, have this form. And the nodal operation does not involve any nonlinear summation operations. It's only a linear summation. So it's illustrated here. The signals pass through the activation functions that has different activation levels, and the node only involves nodal summation. We realize that if we set this W parameter to 1, this becomes a linear path, which goes back to the first example I showed you. And so this seemed to suggest if one was thinking about this type of transmission model, the nonlinearity actually only comes from the probabilistic nature of sending these particles. So this is a very interesting interpretation. It turns out one can, the log sigmoid activation function is not the only activation function one can associate with that type of dynamics. If we restrict our output to be non-negative, we are essentially doing a threshold on this activation output, then one can essentially using the positive part of this curve, one have this form of activation functions. And on the right, this one is just a standard rectified linear unit. If we take a different perspective, the state transformation, instead of taking negative log, here we just take log. Same analysis go through. It's just we get a different nonlinear function here. This we call it a tunable soft define because it's extend the standard soft plus activation function. The extension is as follows. As you look at this curve, it looks as if it's soft plus activation, but it has some negative leaky parts. If we set the parameter W to 0.5, this becomes a soft plus with some offset log 0.5. Another activation come out naturally from this is the tunable sigmoid activation function, where you take the partial derivative of this activation with respect to the signal input. You get this form. Looks a bit complicated, but if you check the figure, it's quite straightforward. Where W0 equal to 0.5, this is the standard sigmoid activation. When W does not equal to 0.5, these curve cross the y-axis. This particular point is highlighted in red here. These are actually the parameter value for W. So this gives you a flexibility of choosing the threshold value, which is exactly the W parameter here. Okay, so this different view of this virus spread model actually gave us some simplified our analysis about epidemic threshold condition. So if we ask the question, will the virus die out as time goes to infinite, regardless of initial conditions, one can identify a condition like this. Basically, all the eigenvalues of this matrix A Hadamard product of W less than 1 in absolute value. This simply means element-wide multiplication of the two matrices. And the analysis is very straightforward. Just one slide. We use the concavity of property of this activation function in its signal input, and we write an inequality condition, and we apply this into the dynamics of the transnet. We get the same inequality, and we set the reference point to the origin. Now we get this inequality. This is on the right-hand side. It looks just a linear summation, no nonlinearities, and we know that this inequality is element-wise. So we know the state Si will be bounded by all the states of this linear system with the same initial condition. And we know the linear system is globally asymptotically stable if the spectrum or all the eigenvalues of the system matrix are less than 1 in the absolute value. So now we sort of have an idea, a very straightforward idea of the threshold condition, which is just this condition. If we specialize this condition to the special case where we have a homogeneous recovery rate. Can
you go back to your theorem?
Yeah.
One more. No, the theorem itself. Yeah. I see. So it's an if, but not an if and only if.
It's not an if and only if. There is a tricky part when this thing equal to 0, equal to 1. But when it equal greater than 1, we can show that there will be some initial conditions. The variables do not die out.
So if you go to your next page,
yeah.
So this proof really only gives the if, right? So this will not give if it's bigger than 1 that you.
Yeah, this is one direction, give one a sufficient condition. The other direction, one should use local perturbations around the origin to get this is one can prove that
okay.
When this thing is greater than 1, there will be some initial conditions where the verbs do not die out. So a special case of this is where we have a homogeneous recovery probability delta, which set the diagonal element of W to 1 minus delta. We have a homogeneous transmission probability or infection probability beta, set off diagonal terms of Wij to beta. And we can explicitly write out this element-wide product in terms of these parameters and the matrix A. And then we get the well-known threshold condition, where this A tilde matrix is the adjacency matrix without self-loops. So another thing we can derive out of this is look at the continuous time model for this transmission neural net. Here, when we look at discrete time version of it, we haven't made any assumptions on the Wij with respect to time duration for transmission. If we make an extra assumption that this thing roughly scales linearly in small time duration, and then take the small time limit, one get the continuous time model. And here, this coefficient Cij is the basic transmission probability rate per unit time from J to I. And Cii is the self-healing probability rate per unit time. This model has a nice, interesting feature is that we don't see product term of Si times Sj on the right-hand side. Now use the same relation between the state S and the probability of infection. We plug this into that. Immediately we get the continuous time network SIS model. But here the difference is that one actually get the product term on the right-hand side. To summarize at this stage, we start with a discrete time variable spread model that has this product form. We take a different view of the system, represent the state as the information content. We arrive something roughly linear or a summation of a nonlinear activated signals. And then with further assumptions on these Ws, how the transmission probability, we assume that is roughly linear in time duration. Taking small time limits, we get a continuous time version of this model. Use the same state transformation that gave us back to the standard network SIS model. So sort of this loop shows you these are actually consistent models as under this assumption. So we can think about this as we mentioned earlier, these are actually neural networks. So we can treat them as learning models. One first question would ask is, are these universal function approximators? Like a set of, it's a universal function approximator is a property of a set of a function. Of a set of parameterized function is called a universal function approximator for continuous functions from d-dimensional input to m-dimensional output. If for any small epsilon, for any compact subset in the input space, any function that defined from this compact subset to the output space, a continuous function, we can identify a member in the parameter size function that is arbitrarily close to the continuous function one chooses. So this means that we can use this set of functions to approximate continuous functions arbitrarily well. Here is an example to illustrate these properties with one transnet with one hidden layer. Take the simple case where we have d-dimensional input, just a scalar output. Here, the structure looks like this. We have the signal inputs. Each of them are weighted by their coordinates. And then coming to the node has a summation form. Actually, we have a fixed bias term that come into the node. The node only take a summation. And then the output of the node gets into these activated links with different activation parameter W. Here, these parameters N and AI and WI and eta I highlighted in blue. These are the tunable parameters. There is an interesting aspect of here is that we associate these linear connections with an activation with level activation level 1. This is also different from the standard universal function approximator result for these structures, where one also require B to be a tunable parameter. So each node will have a different bias term. Here we don't require that because we have tunable activation W here. So for that, if these are the choice range for the parameters, and this model, we can use the same type of proof, show that this is actually a universal function approximator. So here is an example. If you think how to look at this as multiple step or you have several steps neural networks. We treat the same system. We give the initial states as the input. We look at some finite horizon. The output at time t will be considered as the output of this TransNN model. So the objective is then giving these initial conditions as the input data, and we want to compare the observation of the system output with the labels, and then plus some regularization cost. And we want to find the parameter in your parameter set that minimize this cost. Standard view of the supervised learning. And now the observations, we can associate that through our state transformation to link the state back to the probability of that particular node is being active. And we can also pick a small subset of the output through this observation. If you want the input and output to have different dimension. To incorporate this thing to the recurrent neural network structure of the graph neural network structure, which can do similar things. The key is to use these three tunable activation functions. By using these tunable activation functions, one can associate the probability of activation that we start with the widespread model. And the second aspect is to take this link activity states, by which I mean these are the link activity states, and we take the summation. So the advantage of using this as a learning model, as I already explained earlier, that we can have a notion of probability of node being active naturally built into the model. The second aspect is that if you set these parameters, set these activation parameters as part of the trainable parameter, then you get an automatic selection of the activation functions through a range of activations, where some of them actually include the standard activation function as a special case. And then the flexibility of thinking about activation with links, that you can associate a different link with different activation levels. And you can also think about problems where I fix the graph structure and I only tune the activation level for that particular link. So this is the end of my talk. So we discussed TransNN as various spread models. We discussed the threshold condition that easily come out of it. And so this different view of the various spread model naturally link the discrete time version of network SIS model with the continuous time network SIS model. And we also discussed the property of universal function approximator of TransNN as learning models. And I introduced you three different activation functions where that are associated with this structure. And it has the nice property that one can automatically tune the activation functions, and we have natural interpretations of node activation level, node activation probability that come out of the output. So moving on for future work, the first thing I'm investigating is the control and modulation of these models, both in the learning setting and the epidemic setting. So here is sort of the control variables one can associate with the TransNet to view it as a various SPED model. So all these different control variables naturally fit in the framework. In particular, if one think about the case of varying mask, you have an inward and outward efficacy. And so if you multiply the efficacy on the left of Wij, this represents the inward efficacy of the varying mask. If you associate it to the right of the Aij's, representing the number of various particles you send, that means the outward, associated naturally the outward efficacy. One can think about social distancing, vaccination, treatment. The case for treatment is you give a particular way of modifying the diagonal elements of the W matrix. One can also think about the global modulation where simultaneously we change a set of parameters for different links. Another question of interest is to look at the random realizations of these connections and the random realization of the states. Here, the type of model that I present to you as treating these connections as really probabilities, and we propagate the probability, but we never realize these random connections and random states. So there will be some error, and then it's of great interest, both in epidemics and in learning setting. Another important thing is to treat the inhibition and plasticity of these connections, primarily motivated by modeling biological neural networks. An interesting question one can ask, can we use this relation between a learning model and the various SPED model to really learn the various SPED? Respecting the local graph structures given some input-output data. And then another work that I've been doing is to look at if we can, how to apply these same type of transformations or same type of views to more complicated model where one can associate individual nodes with multiple states, the exposed states, recovered states, and associated with feature location and age generation. Okay, so that's the end. Thank you for your attention.
Okay. Questions?
So this was a very interesting talk. My first question, and maybe a comment, is that it might not be so simple to somehow tune this system. So how would you relate this to some data from an epidemic right now? How you know, and what would be the way in which you would maybe try to validate this on some specific structure, or on at least on some specific data series, right?
I mean, this is something I'm thinking about, but one of the things I think would be interesting is that if we sort of do some context tracing, we have some ideas of a local structure, and then I put that local structure in the model, and also I observe some the propagations of the infections and choose that as an input-output data and fit the model for each time step. Maybe that gives us some way to train parameters. I think this is a great question. I don't have a complete answer, but that's just my thought.
Can you go back to the page where the model is defined?
On the previous page?
This is probably that's good. Okay, yeah.
For this one?
Yeah. So for our academics people, what would you call this kind of model? Is P-time is that related heat frost? Or?
Yeah, it kind of looks like a master equation for the, for the epidemic process.
You mean this one? I think there was.
No, not this one, the other one, the continuous time one, yeah.
It's called the mean field, individual-based mean field network SAS model.
Right. So this is a version of a mean field equation. It's a little similar to what we would call a master equation, which basically describes the instantaneous rate of infection. Right?
But the master equation is exact beyond mean field, right?
Master equation is exact in the sense that it completely describes the epidemic model. Right?
Yes, this is some kind of mean field.
Right. So it's not exactly a master equation, but it's master equation like.
You basically want to explore the dependence across different nodes, and then one can write something like this. Otherwise, there will be some correlation term multi-layers.
Yeah. So the good question is so how would you use this type of representation to try to validate your model, right? Or is there some simple way in which you could do it?
Let me ask you about more basic questions. Where do you want to use this TransNNs? What's the are you proposing this as a way to model the spread of epidemics networks, or this is just a new architecture that you're introducing for any learning task? What application do you have in mind for this architecture?
So first, this thing, this architecture that can apply to any neural network. If one is simple trick is what we mentioned here. But the simple trick is that one uses this different view of the neural network architecture, link the activation level to a particular link, and that can be built into any of the machine learning model that is using neural networks. Basically, the key factor is the activation function that can give us a natural interpretation of node being active or the probability of node being active.
Right. But where do you want to use it? Like if tomorrow somebody is going to implement this, so where would be the first place that you try? What sort of learning task do you?
I did some experiment on the image recognition, but that requires lots of engineering to get the features of the image. But that was the first thing that it was I actually tried to see the effect of having a tunable activation function. It turns out to be very good. But for others, I think I was thinking to compare this for studying actual epidemic spread, where one has these independent custody type of models, which actually take into consideration the dependence of cross-stitching nodes, and then this may give us some approximation, and at least this would validate that this was something that's useful. And then for really applying to study an academic problem, I don't have a concrete answer at this stage because it depends on what kind of data that we have. But still figuring that out.
So let me try to understand this for the epidemic model. So what you could think of is that I have this SI of 0 and the SI of k, and I would backpropagate in my network, in my neural network, to learn the weights to actually reproduce the observed epidemics, right? Is that what you could in principle do?
Yeah.
If I had if I knew who was infected at time 0 and I saw everybody who was infected at the end, this should be a way to use the standard neural network technology to have a candidate network.
Right, but you would have to observe your epidemic until the end, right? Or you would have to
and sort of whatever your K is, right?
Right.
I'm not sure of that because if I understand, thank you. If I understand, understand clearly. So Si is related to Pik, which is a probability that I is infectious at time k. So you propagate your probabilities. But if you have data on the path, so it changes because you have conditional probabilities on the path. And it seems to me that it's very nice. I like your talk very much. But it seems to me that can you keep track also of correlations? For instance, if I really know that individual I is infectious, I cannot use my equations anymore because the equation just give the probability of being infectious when I observe nothing. So to answer the question of Amin, I think that I don't pretend to answer the question, but I have the impression that a utility of this model would be first, you have an epidemic and you want to be people more at risk, like in a week, and you could run this this network model, and it tells you, given the possibilities of each individual to be infectious, who would be the more infectious. You could rank your individual by.
So it's more like it's a one-step model, right? It also looks at the next items.
So you're saying it's like you can simulate an epidemic. Is that what
I'm not sure you can simulate an epidemic because if I understand, it does not keep track of correlations or second order information.
Yeah, it doesn't keep track of the second order information, but this thing also gives you an upper bound for the probability of infection for particular model. So regarding to your question that we set this at each time step, we make an observation. I think you're right. At each time I observe probability, I realize the event, and then I should propagate the information starting with the new condition. I think maybe the other idea is that if you know relatively well the connection structure, where this thing does not change that much over time, then you have a fixed structure. Maybe you can use Mongo data to learn the structure and to give an activation link for different connections. Maybe that is a way.
Okay. Other remarks, questions?
So it's really a near field approximation in the sense that
I think it's still different.
It is different because it's not taking into account the sort of the correlations, right?
Write down the
dependence.
network again.
I don't know what type of mean field approximation you're from, but here there are some. If you take these are random variables x's, and these we take random variable xj's, and the point is that we take expectation on the left, and then the expectation cannot come into the product. So here is where the sacrifice on the force expectation to come into the product. And then by that, we are assuming independence.
Okay, right. So in that sense, it's not a mean field approximation because you're assuming independence.
Yeah. Some people call it
More like a tree.
Yeah. So what does it mean, Billy? Does it mean that you have some sort of sparse infection? Because effectively, you are assuming independent. Right? So what does this in terms of graph structure or in terms of some features of the epidemic?
I think it means that if we start from some initial conditions which are initially independent, we propagate one step on the network. The next step, the states, if we treat it as random variables, they are correlated. That depends on your previous, where you sit on the previous states. If you come from the same neighbors, of course, you are related. But if you don't come from the same neighbors, then you are still independent.
Okay, so there is some kind of assumption about the history of the process that says that somehow the dependence or interdependence of these infections doesn't matter for a while.
Sort of like message passing, right?
Yeah,
The messages
that's right.
from your neighbors are independent.
So some type of progress and that's interesting.
I agree. I think it would be interesting to understand when this is a good approximation.
Exactly.
I think that's the standard approximation, right, on the top left.
The standard what?
That's the standard approximation. Yeah. What do you mean?
For who is it a standard? For who it's standard? So what do you mean by standard?
I mean, it's in Mark's textbook. It's. I mean, it's just assuming that it's just taking a product distribution. It's an actual product, right? It's just like 90.0.
So would we expect it to be correct as the network's locally tree-like?
It should be correct on dense networks.
But shouldn't you on dense network actually see the mean field of your neighbors and not?
But that's what he's got. That's what the P.
Or the product of these things is essentially the average effect of your neighbors on you. And then W has to be constant, right? So do you think on G and P, if W is constant, this will be exact? If P is sort of,
If P is O1, then
or maybe log N over N at least divergent degrees. So would we expect this to be exact on dense networks with divergent degrees? It's too bad Mark is not here. So I think this would sort of be good to know.
Yeah, that's right. I'm just not familiar with that particular.
it's just the probability of escaping infection, right? I'm afraid my site is not great at this distance analysis, so I can't read exactly what it is.
Okay, come here.
We're just multiplying the probability of escaping infection from each of the neighbors. Yeah, right? Yeah. Yeah. Standard discrete time model.
Okay. Yeah.
Looking at the actual neighborhood.
So
No, it's not the state of the node, it's the probability. So if you're taking the product, you have to ask whether they're independent from each other.
This is the event of node I being affected.
I see, yeah, if it was a random event, for sure, but you say it's the probability.
Yeah, exactly. So I'm writing this so that I can see this is the computer. If these are random events, what I did right there is take expectations on the left. Right. I take expectation of the right. This is exact. And now the next step is an approximation.
right.
We don't know that, but what we do know is that this thing is less than or equal to the product J. So this is this is
How do we know they're positively correlated?
So there was an observation that if you want to think about, I would like to take the two cases where I want to take I just take two of these, 1 minus x, 1 minus y. This is the probability x equal to 0, y equal to 0. So if I write this as a probability of x equal to 0 condition of y equal to 0 times the probability of y equal to 0. And this thing this means that observe that your neighbors are healthy, and this is the probability that you are healthy. So this wouldn't decrease the probability. I think this should be. So this can be similar. This is and you can do this for all the other pairs. Same argument. But there will be an error which I don't know how to characterize in this case. So this is also something that
How much do we know that on German networks that the probability of being infected are positively correlated?
In SI, probably it is. Simple susceptibility.
Oh, yes, an SI model. Does it have SI or SIS?
maybe
Maybe.
it would have a difficulty if you think about the recurrent state.
Proof, right? Right, if you have recovered, then maybe I see that you are infected, and then maybe that means your neighbors are more likely to be recovered, and therefore I'm less likely to get infected by you. Who knows, right? But if it's SI,
But this is an SI model, so
yeah. So this is probably true. Yeah.
that is model.
Yeah.
All right, very good.
Thank you for the context.
Okay, we get some cookies to get the sugar wake us up for late Friday afternoon.